Welcome to the first lecture on Introduction to Nonlinear Control Systems. In this, we'll be introducing what are nonlinear systems, what are the various methods of analysis of nonlinear systems, why we study nonlinear control systems. So basically, before we talk about nonlinear systems, let us see what is nonlinearity actually. So when do you say that a function is linear? When you encounter linearity and nonlinearity in mathematics, you encounter it with respect to functions. So when do you say a mathematical function is linear? There are basically two properties. You say a mathematical function f is a linear function if it obeys homogeneity, which is also called scaling, which basically implies that f of ax, where a is some constant that is getting multiplied to x, is equal to a of fx. And this is property number one. And property number two is additivity, which implies that f of x1 plus x2 is equal to f of x1 plus f of x2. So basically, a mathematical function is said to be linear if it obeys these two properties. Now, from this, it is very easy to see that functions like fx is equal to 2x would be linear functions of x, and functions like fx is equal to, say, x square would not be linear functions. Now, this definition is extended to the definition of linear systems, and we have already seen this, but this is just to remind you that how do you define linear systems? A linear system described by H that maps an input xt to an output yt is the one that satisfies the property of superposition. These two properties together, these two properties that we just discussed, are basically the properties of superposition. So if these properties are satisfied by a system, which is basically an input to output mapping, then that system is called a linear system. So given two valid inputs x1t and x2t, as well as their respective outputs y1t and y2t, where y1t is equal to h of x1t, y2t is equal to h of x2t, then H is a linear system. H is a linear system if h of alpha times x1t, where alpha is a constant, plus beta times x2t, where beta is another constant, is equal to alpha times y1t plus beta times y2t. This property is the property of superposition, which is actually additivity and scaling. Additivity and scaling said together. So these systems are linear systems, and they're quite simple to analyze, understand, control to some extent. But in general, systems that exist in nature are not linear. Are not linear. So if they are not linear, that means they basically don't satisfy this principle of superposition. And those systems are called nonlinear systems. So this unit is about nonlinear systems. Systems that don't obey the property of linear of superposition. Most of the systems in nature are non-linear. Most of the systems that we see around us are non-linear actually, especially systems that are in nature. So then the question that not automatically arises is, then why do we study linear systems? It is because for practical purpose, uh, a linear approximation works well. A linear approximation of a non-linear function works well, but it does not when but it does not under certain conditions. So for practical purposes, we study linear systems because they're simpler, but in but in there are many instances where this simplifying assumption will not work. When it does not work, we have to study the system as a nonlinear system. So in this introductory talk, we'll be talking about why we study nonlinear control. Why we study nonlinear control systems. Right? So I'll give you a couple of reasons for this, right? So the first thing is improvement of existing control systems. Improvement of existing control systems. So linear control systems rely on the key assumption of small range of operation for the linear model to be valid. If you remember, when we linearize, for example, we have a nonlinear function f of x, and we want to write down the Taylor series expansion of f of x around a point x0. So around x0, you can write this as f of x0 plus f dash x0 x minus x0 plus f double dash x0 by 2 factorial x minus x0 whole square plus so on and so forth. So this is the linear the Taylor series expansion of a linear of nonlinear function around a point x0. So around this x0, you can approximate this function like this. You can write this function like this, and then you can go for a linear approximation. You already seen this, so you can see that your f of x is approximately f of x0 plus f dash x0 into x minus x0. So this is actually the linear approximation of the nonlinear function. We'll talk about this in more detail when we analyze nonlinear systems, but just to tell you what this means. Now, this linear approximation works well. You have actually ignored these higher degree terms. These higher degree terms, the quadratic, the cubic terms you have ignored. And this works well if the deviation from x0 is small. So if x minus x0 is small, is less than some epsilon, that is, it is small, then this approximation is okay. But if if x minus x0 is not really small, that means your range of operation is not small, then your linear approximation would not be good. So your control system design would not be good. So basically, to improve the not to improve the control system design, wherein basically you have assumed that your system works well around a point, and you have a linear model for that point. If the deviation from the linear model is large, then your linear model would not no longer be valid. So this is reason number one. Reason number two is for analysis of certain nonlinearities called hard nonlinearities. Now, the problem is we do this Taylor series approximation for nonlinear functions, nonlinear systems, when we basically we assume that they are the differentiation is possible because you're evaluating the derivatives. But there are certain nonlinearities which are discontinuous, right? And if a function is discontinuous, you don't have a derivative for it, right? So there are nonlinearities that are discontinuous, and these nonlinearities are called hard nonlinearities. An example of, say for example, a discontinuous nonlinearity would be something like if you have a saturation curve which is like this. So it's going like this, and then it's straight up like this. So you have a discontinuity here, you have a discontinuity here, where your f of, say, x minus is not equal to f of x plus. In a similar way here, f of x minus is not equal to f of x plus. So a saturation like this is a hard nonlinearity which is discontinuous. And a delay or a threshold like this, for example, you have this is a delay function. So a delay or a threshold is a hard nonlinearity. You may have hysteresis, which is again a hard nonlinearity. Hysteresis. You have already seen this in when you talked about magnetization of materials, and you may have switches like this, wherein you're switching the function like this and in the positive direction and switching it like this. So you have switches. This is a hard nonlinearity, discontinuous nonlinearity or hard linearity. And you can have another thing called the delayed switching, in which basically you're switching but you're switching with a delay. So you have something like this. So you encounter nonlinearities like this in say for example your machines, electrical machines that you have studied. You encounter saturation in electrical machines. Switches you have seen in your electronics, you have seen in power electronics. You have switches like power transistors, MOSFETs, which basically operate similar to this characteristics that we have shown here, right? So these hard nonlinearities cannot be linearized, and linear approximation is not valid. Even friction sometimes is a hard nonlinearity. So to basically analyze these hard nonlinearities, we need to study nonlinear control systems. And then the third reason is to deal with model uncertainties. Deal with model uncertainties. Now, you assume that when you design in the linear control systems, if you remember what we studied in the last unit, we assume that the model is known. Only then you're able to design the controller for the model or the observer for the model. That means you're knowing reasonably well your A, B, C and D matrices, right? But the parameters of the system change, and your knowledge about the system may no longer be valid, no longer be right. no longer be right. So in nonlinear control, what we do is we intentionally introduce nonlinearities in the controller part. Nonlinearities in the controller part. So that uncertainties can in the system model can be tolerated, right? So nonlinear control systems and its study helps us to deal with model uncertainties, because we are able to do something like introducing nonlinearities in the controller parts so as to be able to tolerate the nonlinearity. So we'll be seeing this more of this towards the end of this unit. And last and an important reason for studying nonlinear control is that we are able to sometimes make a simpler design. So there is a design simplicity. So sometimes what will happen is that a good nonlinear control design may be simpler and more intuitive than the linear counterpart. And this is because the nonlinear control design is more deeply rooted. It's more deeply rooted in the plant physics. So these are four important reasons for actually studying nonlinear control systems. In the next lecture, we'll see what is nonlinear system behavior and how does a typical nonlinear system, how does it differentiate from linear systems. Thank you very much for listening.